countdown, but there we are recording. And what I'll do now is start the screen share, and I'll go to the whiteboard, and I've got to move. Y'all can't see it, but these toolbars or taskbars are just as poorly placed as you can imagine. Okay, so I have to move them out of the way so I have plenty of room to write. And even the bar that y'all are on is somewhat in the way, so I scooted that over too. Now let me move the whiteboard as far to the left and up as I can to get the maximum amount of white space. Okay, now let me get my pad and let's hit it. Okay, so this is page 435. That's what you said, right? Okay, come on. There it is. Page 435. And this is problem set 16.2. And which was the first one? Did you say 9? Okay, so let's do number 9 first. Okay. Find the frequency. So what we're looking for is F. And I can't find my pen, but there it is. F, that's the unknown here. That's what we're looking for. Okay. Of a wave produced by a generator that emits 30 pulses in 2.5 seconds. So you have 30 pulses, okay, in a time of 2.50 seconds. Okay. Now, oops, here comes somebody. I think it's Mercy. Mercy me, it's her. Okay, whoops. There's Mercy. Let her in. Let me mark her as present. Okay, bottom part of the alphabet is doing pretty well. Top part's a little sparse yet. Poor Molly is holding it down all by herself. Okay. All right. Now, for some reason, this showed up, and I didn't want it to show up, so let me get rid of it. Okay. Now, this, don't look for this to be too complicated. This isn't. It's just saying if you have 30 pulses in 2.5 seconds, what's the frequency? Well, the frequency would be, well, I've been calling cycles per second, but that could also be called pulses per second. So basically what you do is put 30 pulses divided by 2.50 seconds. Now notice I didn't put a unit there because a pulse really doesn't have a unit, but time does, so that would be, yuck, I hate it when it does that. That would be seconds, okay? And then if you grab your handy dandy calculator, which is my phone, which I've been on all afternoon, but I think, yeah, I've got enough charge, okay? And that would be 30 divided by 2.5. You don't have to put the extra 0 there. The calculator knows. And that's going to be 12 is what I got. Did y'all get it too? Whoops, I'm writing on the wrong thing. Okay, and that would be 12 per seconds, s to the minus 1, which is the same as 12 hertz. Now, if that's what you got, I think it's correct. What did they have in the back? Did they have it? I'm sorry? I lost you there. Okay. I think I have it marked too. Let me see if I can find it. Probably not as quickly as you can. 12.2, number 9. Oh, that's not it. 16.2. I'm in the wrong chapter. 16.2. Number 9. I got 12.0 hertz. Now I wonder about that part. Okay, I was going to say I see no reason to do. Now I guess this is what they're saying. Since that is 30 pulses, that means that's exactly 30 pulses. So that means you could put as many zeros after it as you needed to. And since you had a 3 digits here, you can make it there, because 30 pulses is either 30 or it's, okay, that's a fixed number. So I question this, but then that could be written as 12.0 or 12.0, and that's what they have in the back. Frankly, I think 12 would be adequate because they didn't give you a 0.0 after 30, but I'm not going to argue with them. 12, don't they have hertz or do they have per second? I think they have hertz. Okay. Does that make sense? Does that answer your question? Okay. Was there another? Which one? 13. Okay, you love the frequency ones, don't you? Okay, let's see. Well, I've got to get my pen in place. Here it goes. 13. That's supposed to be a 1 there. Okay, 13. Find the frequency. So again, what we're looking for is frequency. We've lost it somewhere. Of an electromagnetic wave. Now, as soon as you see electromagnetic wave, you can write something down. You know what it is you can write down? The velocity of that wave is equal to the speed of light, which is equal to, and this is in the metric system, so that's 3.00 times 10 to the, I'm pretty sure it's 8th, isn't it? Meters per second. Let me go back and just make sure. That was on page 433. Back when they give you the speed of light, it's 3.00 times 10 to the 8th meters per second. Okay? As soon as you see electromagnetic wave, you can write it down. Any other kind of wave? No. You have to figure out what the speed is. Electromagnetic wave, they'll usually not give it to you. You know it's the speed of light. Okay? With a wavelength, that's your lambda. And the lambda here is 1.50 meters. This is aggravating. Okay. Okay. 1.50 meters. Okay. Now, do you know a formula that relates frequency, speed, and wavelength? Your units will almost do it for you. But if you go back that same place I just said, in fact, yeah, let's go back there. And on that page, on 433, you see the formula near the bottom of the page there that says C is equal to lambda F. And again, your units always do it. Lambda is in meters, frequency is in per second, so this is meter per second, and that's what speed is. Okay? Meters per second. So we're looking for frequency here, so what we'll do is divide both sides of the equation by lambda, and the lambdas go out here, and frequency then would be equal to frequency would be equal to C over lambda, which would be 3.00 times 10 to the 8th meters per second divided by 1.50 meters. Okay, meters go out, they cancel out, and you know that 1.5 will go into 3 exactly 2 times, right? You don't even need a calculator for this one. That'd be 2.00 times 10 to the 8th. And that would be per seconds, 1 over second. You could write it as s to the minus 1, or you could write that as 2.00 times 10 to the 8th hertz. That's a per second. Yuck! Okay. Is that what they had in the back? I think I've got my paper in place now, so I should be able to see. Number 15, I believe it was. No, wrong. Okay, there it is. Why am I not seeing it? Oh, 13, that's why. 2.00 times 10 to the 8th hertz. And you can also, if you got your book open on page 434, you could see that a wavelength of 1.5 meters, and that would be halfway between, you see the 3 down there and the thing to the right, it's approximately halfway between that. Go up and you have, yeah, something like on the order of 10 to the 8th. So that makes sense. The frequency would be cycles per second or per seconds, which would be hertz. So 2.8, that sounds reasonable. All right, good deal. Any others? All right, okay. Now, still just the 3 of us. No, 4 of us now. Yeah, I got 4 of you. Any other questions before we get going where we left off last time? Okay. Now, where we were last time, I'm going to clear the screen unless you need it up there a little bit longer. Anybody need it? Okay, the one we did last time? Okay, I'm not at all surprised. I don't know if you remember this or not, but I was complaining, maybe you had already gone, that my previous class, the linear algebra class that I had taught, when I finished teaching, I could not find the Screencast-O-Matic anywhere. This is the icon for it. I could not find it anywhere. I finally did, and I told it to end. Okay, and I thought I typed in yes, I think I did. I typed in what I wanted it to do. Then when we did our class, I went to start it, and lo and behold, the one from that morning was still running. So basically, I think I wound up doing on top of that. So there was linear algebra, then a big bunch of dead space there, probably everything I did on my computer you could see, and then there was this class. So I tried to fix that, editing it, and I thought I cut out and saved the Math 1 237 class, but then later when I went to look at it, it looked like I had this class on there and not the 237. So I changed the name to this. But the first part will probably be a lot of dead time, but if you wait long enough, you'll probably see the rest of this class. Now, whether it all got on there or not, I'm not sure. But you couldn't see any of it? Oh, really? Okay. Yeah, because in this class my microphone went out, didn't it? Okay. Well, that may have ended everything. For some reason, the electronics have been so bizarre. It happened Thursday in this class. It happened yesterday in one of my two classes yesterday. I think it was the second class yesterday. It just, I mean, I was going along, they could hear me, I could hear them, and all of a sudden they said, "We can't hear you." And I could hear them loud and clear, but it just quit. It just quit. And so I had to take off the headset and just teach from the microphone, which was sort of a pain in the neck, but they could hear at least there. So we finished the class like that. My wife came in last night and she fixed it on Thursday. She fixed it again last night. So I can't swear that it's going to continue, but it's worked okay today, but it worked okay Thursday for the first two classes, and then just decided to quit on this class. So we'll see. We'll just hope that it keeps working. But I didn't know that it stopped early, so I may have deleted the class from the last time, and I apologize if I did that, because I just assumed that recorded all of the last class. But if it stopped when the microphone stopped, I didn't. Usually those are not connected at all. The Screencast-O-Matic has nothing to do with the microphone. So why it would have stopped there, I don't know. So the electronics have been doing weird things. Today, I had in my second class, I think it was, my internet. Well, in the first class even, it did this. It said, "Internet is weak," or something like that. So I quit talking, waited, it came back on. They said they could hear me, and we went on. The second class, it said it was weak. I stopped talking, I waited, it came back on, I continued talking, and then in a few minutes it just shut itself down and just started searching for the thing, and my internet went out. The screen said no internet. My internet down here at the bottom, like right here, said internet access, but the screen didn't say internet access. It said I didn't have any. So we lost probably 5 or 10 minutes this morning when there was just no, it had to have been a Zoom problem. It wasn't an internet problem, because the internet was here, everything was here. Zoom screwed it up again. And I don't know why. I think my opinion is that the infrastructure, Zoom's infrastructure, the Spectrum infrastructure, that's our service provider, everything is just being pushed to the max, because I don't think they were designed to handle the load that's having to handle with the COVID-19. So unfortunately, that kind of stuff seems to be happening. And that may be why Screencast-O-Matic screwed up, because it just couldn't handle the load. I don't know. You wouldn't think that would be an issue, but may have been. All right, sorry if I did delete something that you can't see again. I didn't delete from the other. It sounds like it just stopped recording, and I didn't know it stopped recording. But I would have left the old recording out there if I'd have known it didn't carry it. But we'll pick up and go from here. Any other issues, questions, concerns? Anybody? Okay, do you need this on the screen any longer? Okay. If not, I couldn't hear it. It sounded like someone was talking in a barrel or something. Can you hear me? Jalen, I see your light on, but I don't hear anything. Are you talking to me? Flash your microphone on and off if you're talking. Your microphone's off now. Now it's back on. Are you talking? Oh, now I can. Okay. Okay, you're fading out pretty badly. Okay. So it's all right to clear? Okay, I hear no objections. Okay, so I'm going to clear the drawings. Let's pick up where we left off last time. I was starting to do the definition of pitch. So let's do the text again. Okay, I'll set my pen down and type it in here. The pitch of a sound is the effect of the frequency of sound waves on the ear. Okay, so this isn't quite a technical term. It sounds like it would be, but it really isn't quite so much a physics term as it is a qualitative term. The effect of the frequency, that's supposed to be a space between those, of the sound waves on the ear. So you hear the pitch. That's something you hear, qualitative. Probably isn't measured very precisely in any way. It's just what it sounds like. Frequency is measured very precisely. That's a technical term, the frequency. The pitch is the effect of that frequency on your ear. Okay? Sounds like it's sort of picking points there, but that's what it is. Now the next thing that's in your text, and I'm not going to draw it, but let me show it to you. Here is this really nice illustration of the human ear and how it's put together. And there is a little bit of a discussion in that. We're not going into that in gory detail. I don't think you need that for your diagnostic medical sonography, but that's what that shows the ear. It's an amazing, amazing, amazing instrument. That little membrane there that we often they call it the tympanic membrane, is called the eardrum. That's the common name for it. That's what vibrates with just little bitty vibrations. And that makes a vibration there. It's amplified in the malleus and incus. You see just above there, they're called the middle ear. The eardrum or the tympanic membrane is kind of the boundary line between the outer ear and the inner ear, or middle ear. And then, so this amplifies that. It's sort of like a hammer and an anvil there, the malleus and the incus. And they are connected to the cochlea. And the cochlea are where most of the nerves are connected. And again, a lot of amplification goes in there. And I believe, if I'm not mistaken, inside the cochlea are these little bitty cilia, little bitty things, and the vibrations make them move, and that's what sends the message and distinguishes things like pitch and other things like that, quality of the sound, to your brain, and your brain figures it all out. How in the world, I'm not sure. Okay, what your nerve endings are picking up are little electrical signals. So basically, you're an electrical machine. Your nerves are carrying those signals to the brain processes those signals, and that's what makes you hear. And it's done instantaneously. I mean, just amazing, the complexity. We are fearfully and wondrously made. It's just amazing. I did want to point about a couple things to you. I'm going to set my pad aside for a moment here. The cochlea, for those who may have had, if you've ever had a child in your family that is deaf or very hard of hearing, they can do things like called cochlear implants. My wife works she's a epidemiologist at UAB, and she works with the disease, cytomegalovirus, that one of the major results, or they call it sequelae of this disease, is the fact that it can cause hearing loss in young children. And quite a few of those kids that have the hearing loss have the cochlear implant, so I hear them talking about it. But also another thing, you'll see that eustachian tube that goes down, it's behind the eardrum, it's in the middle ear, it goes down and goes down into your throat. Okay? Now, just to give you an idea of what that does, that's a pressure regulator. It doesn't affect your hearing per se, but it enables the pressure to remain the same on both sides of the eardrum. If the pressure got out of balance there, you could conceivably break the eardrum or puncture it or have a problem. Now, young kids, especially if they get, say, a cold or something like that, and their sinuses and other tissues swell up a little bit, because their eustachian tubes are so incredibly small because they're young kids, and then you get some swelling, it closes them up completely. Then the pressures can't equilibrate on either side of the eardrum, and therefore they get incredibly intense earaches. And when they have them, they scream bloody murder. Okay? I don't know if any of you have had kids or younger siblings or something and have witnessed this. It's a terrible thing for those kids. And sometimes they'll go in and put in tubes to help equilibrate that, because that's necessary. Now, have any of you ever been in an aircraft, especially a jet aircraft? Have you ever flown? If you have, when you take off, Jalen, were you going to say something? You have. Have you ever noticed when you're either taking off or coming in for a landing that your ears pop? Okay, that's the eustachian tube. When you're changing altitude, you're under different pressures. Your inside the ear is still at the pressure you were at. The outside the ear is now at a lower pressure if you're going up, or a higher pressure coming down. And in so doing, you get these pressure differences, and your ear will sometimes pop because your eustachian tube isn't able to equilibrate that fast enough, because you're not used to going up and down that rapidly. Now, this will also happen, I've had it happen in a car before, when you're going up a fairly steep incline, as in climbing a mountain. But not just any old mountain. Up in Coleman County, I believe, there's some of those hills are really steep. I've actually had my ears pop on those too. Same deal. Of course, if there's a kid on that plane and their ears can't pop, their eustachian tube is too small and can't equilibrate, then they feel the same effect that they would if they had a cold and the eustachian tube swelled up. And that's why the kids will be screaming bloody murder, especially when they're climbing or coming down, because in either case the pressure gets out of balance and the eardrum is feeling that pressure, the pressure difference. So I wanted to point that out to you too. The other thing, and this is yet another issue, notice all the bone material that are around there. That also contributes to what you hear. Okay? And here's a question I have for you. Have any of you ever heard a recording of yourself? Yes or no? Yes. Did it sound like you to you? No. Everybody else sounds like themselves, but you don't sound at all like yourself. Okay? To you. This happened in our family. We had real good friends, and this couple came and visited my parents, and they were sitting around talking. It was around Christmas time, I think, and Andy Anderson had brought as a gift to my parents a tape recorder. Now, this is old technology. Anything as good as we have. But rather than give it to them, he just started it running under the table when they were sitting around the table talking. And my dad almost died when this happened, out of laughter. My mom, when Andy played it back to him, she said, "Who's that doing all the talking?" Of course, it was her. She could recognize everybody else's voice, but she couldn't recognize her own. And here's why. You hear, when you're talking, most of that sound gets transmitted not through waves that go into your ear like this. It gets transmitted through the bones in your facial and cranial structure. So that's what you are hearing you sound like, but everybody else is hearing the vibrational sound, and they aren't necessarily the same. And this is just a theory of mine. I haven't ever seen this done. I bet you somebody knows it exactly. But when you hear of somebody who has perfect pitch, a singer who has perfect pitch, that's because their bone structure, in my mind, is transmitting exactly the same sound to them that everybody else is hearing. So when they're singing on note that they hear, they're also on note that everybody else is hearing. Everybody else is probably a little off, okay? If you don't have perfect pitch, it probably doesn't sound quite as good. All right, too much of that. But just to other issues there. Now, for some reason, the text did not come up. So let me see if it'll come up this time. There we go. All right. They're now moving into 16.4. And this is the Doppler effect. And that's what we're talking about now. The Doppler effect refers to the variation of the frequency that's supposed to refers. Whoa, what in the world is it doing? Okay. It's supposed to be an F in there. And somehow to me, it's all gotten all screwed up. But we'll live with it. Okay, I think my wife just came home. If she did, she'll want me to close the door. So hold on just a moment. I got to take off my headset. Try not to put any stress on any of my electronics here because they seem so very sensitive. So, can you hear me? Anybody? Yeah, okay, good, thanks. Okay, so the Doppler effect refers to the variation of the frequency heard when a source of sound and the ear are moving relative to each other. Okay, hope that, woo, missing an N there. Okay, now this is way too big of type because for some reason it just started typing bigger. And I've covered the place where I could maybe adjust it, but I'm going to leave it alone. Okay, that's what Doppler effect is. Now, you've probably noticed it before, but I'm not sure you knew what it was when it was happening. Have you ever been, say, at a railroad crossing when there's a train coming and the train is blowing its whistle or horns or whatever it is that it blows to try to warn people not to be crossing, because the train's going at a high rate of speed and doesn't want to hit anybody because it wouldn't possibly be able to stop in time. So it really lets out a thing. If you hear that, you'll notice two things. Don't get them confused. One thing, it gets louder the closer it gets because it's coming toward you, of course. But not only does it get louder, it goes up in frequency. Okay? The pitch goes up. You sense a higher frequency than what it's really doing. And the reason is because sound waves are pressure waves. And if it was sitting still and making a noise, then all the pressure waves would be the same distance apart, and it would sound all at the same frequency. However, since the train's coming at you with a rapid rate of speed, the sound that it's emitting, the sound waves get pushed closer together because of the motion of the train. So now they have a higher frequency. Shorter wavelength, higher frequency. That's the Doppler effect. Okay? When it goes the other way, the train's going away from you but still making its noise with its whistle or whatever, now the pitch seems to go down. Now, the volume will go down too because it's getting further from you, but the pitch, the frequency, also goes down as well. Okay? So that's what the Doppler effect is. Okay? Now, you'll see in this sometimes in other contexts. If you've ever watched the weather, especially when you have severe weather in the area on TV, you'll hear them talk about a Doppler radar. And that's doing the same thing. It's measuring the change of frequency when the wind's coming to you or when the wind's blowing away from you. And if they get on one place, it's coming to you, maybe that would be a red color, but on the other side it's going away from you, that indicates rotation. That's a good indicator you may have tornadic activity. Okay? And that's why they use Doppler radar. But, you know, thunderstorms also have rotation. They don't have to be a tornado, so they have to determine how tight that signal is, whether it's actually tornadic activity or just a thunderstorm. Okay, so that's the Doppler effect. Now, notice it's an apparent, it's what's heard. Again, a pitch type thing. Not really, the train is not increasing the frequency of its whistle. That's constant. But it is sounding like it's increasing because of the relative movement between the source of the sound and your ear. Now, if you were moving rapidly toward a constant sound, you would also hear it go up in pitch. And if you're moving away from something rather rapidly, it would also sound like, even if it was at constant frequency, it would sound like it's going down in frequency, down in pitch. Here is the formula that describes that. And since I'm not going to be able to type this in so it makes any sense, I'll write it in. So let me get my pad and my stylus back so I can write it in. What F prime is here is the apparent frequency, what you think you're hearing. Okay, that's the Doppler shifted frequency, not the real frequency, the Doppler shift, the one you hear. That's equal to the actual frequency of the source. Source is doing at a fixed frequency, you're hearing a different frequency. That's the F prime. And here's what you multiply it by that produces that change. It's the velocity of the sound, the speed of sound, divided by the speed of sound plus or minus the speed of the source, V sub S. Okay. Now notice frequency on this side, frequency on this side. You better not have any units in here. Well, velocity on top, velocity on bottom, meters per second, feet per second, whatever. It's going to be the same, so that it's not changing units at all. This is just a ratio. Now, why is there a plus and minus there? The plus sign in the denominator is used when the source is moving away. Okay? The minus sign is used when the source is moving toward the receiver, your ear. Okay? Now, here's why that's true. That may sound a little bit sort of like a contradiction, or why is that the case? But think about this. That sign is in the denominator. So that's an inverse relationship. If you have a bigger number in the denominator, that makes for a lower frequency here. That's why your plus sign is when you're moving away. But when you have the minus sign down here, that decreases the velocity. Okay? So a smaller velocity here makes for a higher frequency there because it's an inverse relationship. Okay? So that's how you can maybe help remember that. Let's get out of this for a moment and see if we can, if they do have, this just hacks me off so much. I open here, I'll have to open them again. Chapter 16. I still don't see chapter 16. Where is, oh, there it is. This must be it. There it is. Okay. Let's go down to where we are now. Oh, goodness gracious. There was our ear. Okay, let's go back to this. I was showing you in the thing, I forgot it was on the slide set. From current slide. Okay. So this is what we're talking about. This is the ear you see. This is basically, this is like the reverse of a cone. This channels the sound vibrations into the external auditory canal. Your ear acts like a megaphone in reverse. It's capturing the sound and sending it into your ear. Hits the eardrum, the tympanic membrane, and that vibrates, and the malleus and incus back here respond to those vibrations, sort of like a hammer and an anvil, okay? And they transmit the sound to the cochlea, which is here. Now this is the middle ear, the cochlea in the inner ear, that's the boundary there. The membrane is the boundary on the outside, this part of the cochlea is the boundary on the inside. And then this is where all the a lot of the processing goes on. The nerves pick up all the signal from both the membrane and the cilia and the hammer and anvil, the malleus and incus. All this stuff is probably amplified, processed in here, and those signals are sent to the brain. The brain then puts it all together instantaneously, it seems like, and you hear. Okay? This is the bone structure I was talking about. This is what transmits the vibration that you hear of your voice, but other people hear what comes in from your the vibration, the sound vibration, the air compressions and rarefactions. Very different from what, well, sometimes very different from what you hear through your bones. Okay. And I think that's mostly what that was about. So let's move on down. And here it is. This is on the top of page 440. This is figure 1620. The car is moving to the left, and it has a horn going on, and the horn is a constant frequency. But because the car is moving, that pushes the sound waves closer together, so it sounds like they're going up in frequency to the guy over here at A, but it's going down in frequency to the gal over here at B, because now the sound waves are further apart. It's the same horn. He hears a high frequency, she hears a low frequency, because the car's movement compresses the waves on the left-hand side, rarefacts or makes them further apart on the right-hand side. So she hears a decreasing frequency, he hears an increasing frequency. That's the Doppler effect. The horn is something in between what he's hearing and she's hearing, and it's by that formula we just did. Okay. Now, let's do example 1. And by the way, y'all can see that figure, couldn't you? Let's go to the whiteboard. An automobile, let's go on and clear this screen. Sort of be nice to leave that formula here, but we'll draw it back again. Clear the screen. An automobile sounds its horn while passing an observer at 25 meters per second. Now that doesn't sound too much. That's going pretty fast, by the way. Okay, so this is the speed of your source, V sub S. That's the source of the sound, not the sound itself, but the source of the sound, and that's 25 meters per second. Okay, the actual horn has a frequency. So here's the actual frequency, the real frequency of the horn, F, not the observed frequency, not the Doppler shifted frequency. The actual frequency is 400 per second, or hertz. And a hertz, remember, is a 1/second, or a second to the -1. Okay. Assume the speed of sound is 345 meters per second. So this is V, the speed of sound, at that temperature and that moisture and everything else is 345 meters per second. Now if you turn back to your earlier situation when we were actually calculating that, remember at 0 degrees Celsius it's around 331 under normal conditions. So this is considerably higher velocity of sound, meaning you have a higher temperature. Okay, you're not at freezing, you're somewhere probably closer to room temperature. Okay, now the A part of the question here then, whoops, I'm trying to write on the screen. The A part of the question here is, what is the frequency heard by the observer while the car is approaching? So this is F prime. Now this is as the car is approaching the observer. Well, your F prime here, the perceived frequency, the Doppler shifted frequency, is your frequency of the horn times the velocity of sound divided by the velocity of sound, and here we have to decide plus or minus. Right now the horn is, what is the frequency heard by the observer while the car is approaching? So the car is coming to you, so now we use the minus sign, V sub S. So it's coming to you at that speed, 25 meters per second. So let's do it. The actual frequency is 400 hertz. I'll just leave it as hertz. Okay, times the velocity of sound at this temperature and stuff is 345 meters per second divided by 345 meters per second. It's supposed to be the pen isn't writing well, minus 25 meters per second. Okay, now want to remind you of something. If you're multiplying or dividing, you keep up with your significant digits by how many digits you have. When you're adding or subtracting, you go with whatever the last digit is. This is the ones digit, there's the ones digit. So we'll go to the nearest ones digit, okay? So what this gives you, if I get down on my right pad here, this would be 400 hertz multiplied by 345 meters per second divided by 345 minus 25 is 320, right? Meters per second. Now notice both of those have the same units, they cancel out. The units cancel out, so you multiply by the ratio of those speeds. So that would be, let me get my calculator up here, and that would be, oh, here it is, 400 times multiply by 345 and divide by 320. And I get 431 and a quarter, but because a quarter is less than a half, I'll just make that approximately 431. Yes, it did shift it. Whoa. Yeah, it shifted it up. It was 400 and now it's 431 hertz. 3 significant digits here. I forgot to put my bar over here and here. And this is 3 significant digits. Even with this, even though that's only 2, when you subtract it from it, you get 3 significant digits. That 0 is significant. I'll put the bar over it so you know that it is, and then that gives you 431 hertz. And that's what they got. Okay, that's the A part. However, the B part is asking, what is the frequency heard when the car is leaving? And again, okay. So when the car is leaving, it's going to be the B part. And when it's leaving, your perceived frequency, the Doppler shifted frequency, is the same frequency of the horn times V over, but this time V plus Vs. And the car is going at the same speed, so this will be 400 hertz times, yuck, it'll disappear in a minute. Okay, you probably can't see it anyway. 345, again, meters per second, divided by 345 meters per second. But this time it's plus your same speed, 25 miles per hour, meters per second. 25 meters per second. Okay, so this will be the new Doppler shifted sound would be 400. I forgot to put my bar over it. 400 hertz times 345 meters per second divided by, this time you add the 2, and that's 370, I think, right? So let's pull out our handy dandy calculator and see what we get this time. 400 times 345, but this time divided by 370. And I got about 373 hertz. Got the wrong end of the pen. Okay. Let's see, where is my cursor? Come on, there you are. That's approximately 373 hertz. So the frequency went down because the car is moving away from you now. Let's see how the book did. Yep, they got 373 also. Do you see how Doppler frequency works? All right. Now, that finishes, or almost finishes, the section. One pretty major little blurb here on physics connections on page 441. Now, if you don't have your book, it's well worth a read. This is what, not exactly what you'll be doing. This is a diagnostic medical sonography for fetuses. I think y'all are entering a program that's going to be doing blood, right? Blood flow. That's same principle, but different frequencies. Okay, different. You're looking at different dimensions there than what you have here, but that's well worth a read here. Okay, and you see actually a three-dimensional ultrasound of that human fetus. Don't know if it's the same one she's taking there, but it looks like it could be. Okay. Now, that finishes then 16.4. You can do any of the odds 1 through 5 on page 441. And then on page 442, any of the odds 7 through 19. Okay. Okay, on 441, any of the odds 1 through 5. And then on page 442, any of the odds 7 through 19. Did that come across okay? Could you hear? Okay, good deal. All right, now the last thing we're going to talk about in this, well, no, it's not quite the last thing. But the last thing that really is directly related to sound is a thing called resonance. Okay, so I'm going to clear the screen here if it's okay, and let me type in a couple of definitions. Okay, let's get my text in place. Okay, the natural frequency of an object such as, left off my U, a tuning fork. Don't know if y'all are familiar with those. Okay, is the frequency at which it vibrates when struck by another object. Oops. Okay, I believe that's where the period goes. Okay, nope, they have such as a rubber hammer. I don't know if that's necessary, but I'll type it in. Okay, period. Okay, let's string that out so you take more efficient use of the space here. Okay. Okay. The natural frequency of an object, such as a tuning fork, is the frequency at which it vibrates when struck by another object. Okay. Now, tuning forks, the reason they give them that name, they're very precise instruments. They're made out of a certain type of steel that has a very certain elasticity. So when you strike it with, say, a rubber hammer or something like that, then you'll hear it, and it'll be a very pure note, very pure note. The frequency in between those is just so that it gives a very constant. So if you're like tuning a guitar, a piano, or anything such as that, that gives you, say, your middle C or whatever note it happens to be. Okay, that's what a tuning fork is. It's used to tune a musical instrument generally. Now, the sounding board on a guitar is forced to vibrate at the same frequency as all the strings because the energy transfer from the strings to the sounding board, that's what they call a forced vibration. Now, I'm not going to type that in because that's sort of complicated sounding. But the next word I do want to type in is what the title of this section is, which is resonance. Okay, and let me get this here. All right. This is called sympathetic vibration or resonance, and here's what that means. The resonance, or I'm sorry, resonance occurs when the natural frequency that we just talked about it's the same thing, but they call it natural vibration rates, which is frequency, of two objects are the same. Okay, now what that's not sane but same. Whoa, goodness gracious, that whole, I had one hand completely off. Right hand was not in the right place. The vibration rates of two objects are the same. Okay, that time it came out right. Sorry about that. Okay, let me expand my box a little bit there so it'll take up better thing. Now, what do we mean by that? Well, this is what they mean by tuning a musical instrument. If you have say a middle C, you're trying to do that on the piano. Now, I don't do it. Someone who knows how to tune a piano would do it. He strikes with the hammer, rubber hammer, the tuning fork, and it makes a certain sound, and then he adjusts the frequency, the tension in the piano string that's supposed to be the middle C frequency, and that the moment when it starts vibrating on its own at the same frequency as the tuning fork, you know you've hit it on the nose. Okay, you do the same thing. Are any of you guitar players? Let me just ask that. Yes or no? No? So far, I haven't had a single guitar player in my class. I'm not either, so I'm not casting dispersions or anything. But when you're trying to tune a guitar, say if you have a piano in tune, you hit the note there, and then you try to listen to when the guitar, you adjust the vibration of the string that you know is supposed to be that note, and when it starts vibrating with the piano key, then you know you're on frequency, because their resonance occurs when the two vibrations are, one makes the other happen. Okay, that's resonance. All right, now people who have really good ears can just get them to do, and then once you get one string right on the guitar, you know where that same note is supposed to be on the next, and you put your finger down on the fret and you get those two to vibrate at the same time, and then you go on down and do your whole setup that way. I know the theory of it, I just can never do it. My ear is not that good. My mom could tune them in no time. She had a great ear for music. I didn't. So even when I tried to play, I could tell when something was off, but I couldn't tell what was off about it. I just knew it was off. When I was playing the piano, I always would look to the wrong hand. I knew the sound was off, but I couldn't tell which way it was coming from. Okay. This, let's see. No, this isn't in the slide set, so let me show it to you. This is one tuning fork, the other tuning fork at exactly the same frequency. You strike the first one with the rubber mallet or whatever that is, it sends a signal to the other one and it starts vibrating on its own. They're not connected at all, but it starts vibrating with the other one because they are at exactly the same natural frequency. So they will vibrate, resonate with each other. Okay? Now, I don't know if you've seen anyone do this, but if you have a good piece of crystal, they say wine glass, it doesn't have to be a wine glass, it could be, well, where is it? Where is it? There it is. Okay. And you wet your finger and run the finger along the top of the wine glass, it will resonate and make a really high-pitched singing noise. Fill different glasses with different amounts of water, they resonate at different frequencies. And I don't know if you remember, but there was a dumb movie with Sandra Bullock in it named Miss Congeniality. Anyone see that one? She was an FBI agent but going undercover in a beauty pageant to try to find out who was going to direct the pageant. And the only talent she could come up with, except throwing her partner around, which she ultimately did, was she was going to play singing wine glasses. She had a really good ear, so she fixed the wine glasses, filled them with water, you know, at different levels, and she could play a song on them. Well, the other contestants thought the water was there for them to drink, so they drank her talent thing. So then she threw her partner around. But anyway, that's a dumb thing. But that was what they meant by singing wine glasses. With different amounts of water, they resonate at different frequencies. Okay. All right. So let's move on to 16.6. There weren't any problems in 16.5. Let's move on to 16.6. Now, 16.6 is talking about simple harmonic motion, and that is actually the first definition they have. What in the world do we mean by simple harmonic motion? Is a type of linear motion in which the acceleration of an object is directly proportional to its displacement from its equilibrium position. The motion is always directed toward the equilibrium position. Okay. All right, quite a long sentence there. Okay, let's see if we can decipher it and make some sense out of it. Okay. Let me preface this with this. Most things in nature operate according to simple harmonic motion. If you think about it, daylight, darkness, okay? Almost simple harmonic motion, okay? Your pattern, daylight, darkness, you think of a sine wave, okay? Now the harmonic part of this sounds like music, doesn't it? That's exactly what it's meant to sound like. Simple harmonic motion, you're getting into the rhythm of whatever you're dealing with, okay? type of linear motion in which the acceleration of an object is directly proportional to its displacement from the equilibrium position, and the motion is always directed toward the equilibrium position. Now, I don't really like that last clause too much. It should be the acceleration is always directed toward the equilibrium position. Okay, now here's an example of it. Let's say you have a pendulum, a mass hanging by a string, and you lift it up over here, okay, and then release it. It's going to go toward the equilibrium position, which is directly under here, but see, it's picking up speed as it goes. It's accelerating toward the equilibrium position. But then when it reaches it, it starts decelerating, meaning the acceleration is back this way, but because it had such a high velocity, it keeps going here, slowing down until it reaches its peak here, and then comes back down. Again, always accelerating toward the equilibrium position. Not the motion always directed toward it, the acceleration is always toward it. I wish they had done that. In fact, I think I'm going to correct that and put acceleration. Okay. It's always directed toward the equilibrium position. Okay. Now, if some of these terms that I'm going to type now sound familiar, they should. We measure things using the same type terminology. Okay? The displacement of an object in simple, that got off, didn't it? Harmonic motion is its distance from the equilibrium or rest position. Okay. Now, remember before we talked about waves in general, and that was a displacement from an equilibrium position. So it's the same type concept here, okay, only we're talking about equilibrium. We're talking about simple harmonic motion. If this is the equilibrium position here, the displacement is how far from that you are. How far up the arc you are here or wherever. That's your displacement. When you're at the equilibrium position, your displacement is 0. Okay? Now, the amplitude, and again, this is very familiar sounding words here, same words we used before, of the vibration is the maximum displacement, and I'm not going to write that, and now we're talking here about the Ferris wheel, so I'm just going to leave it displacement, okay? I think what I'll do is go to the other slide. Whoops. Okay. The amplitude of the vibration is the maximum displacement. When I was talking about a pendulum, the maximum displacement, that would be its amplitude, as high as it will possibly go. When it comes down and goes back in the other way, it'll go to the same height. Maximum displacement. Okay? Now, the period, I'm going to show you the slide in a minute, but let's go on and get the words in here. The period is the time requirement, just like it was before, for one complete revolution. Now they're talking about the Ferris wheel. I'm just going to stop it there. I'm going to say revolution. I would say one complete path, maybe, okay, which is the same as a revolution on the Ferris wheel. Okay, and that's a period. Okay, I don't know where the N came from. Not even close. Okay. Time required, just like before, the period is the time. And of course, then the last term is frequency. Is the number of complete vibrations per unit time, or the number of complete revolutions that you make. I'll just leave it like they're talking about a Ferris wheel. We'll show you how the Ferris wheel works, okay, and how it fits in with this. Okay. Frequency is the number of complete vibrations. That seems redundant to call it complete vibrations per unit time, or the number of complete revolutions that you make. Okay. For the pendulum, that would be from here, if you started here, to it goes down here, up here, and back to the same initial starting position. That's one complete cycle. Okay? One complete vibration per unit time. Okay. Now, with those definitions in mind, let's now go to the Ferris wheel. Okay. Okay. Go from current slide, and we'll go one past that, and there's the Ferris wheel. Now, this is kind of a strange example, but it actually works quite nicely. Now, the sun is shining down on the top of the Ferris wheel. Odds are it's not shining completely down, but we'll just pretend that it is straight down. Okay? In other words, this is your own inside the tropics, and the sun's directly overhead shining down. Okay? And here you sit in the Ferris wheel. Okay? And what you're going to be looking at is your shadow. Your shadow from the sun's rays. Right now that shadow is right there. A few seconds ago, if you were down here a few seconds ago, it would have been out here at Q. Okay? But as you go up, your shadow goes here, here, and when you're directly overhead, your shadow is right there at 0 prime. I don't know why they put the primes there. Okay? And then as you continue on here, your shadow goes over here until it reaches P, which is directly underneath where C is right now, C prime, and then it starts moving back again. So your shadow goes in simple harmonic motion back and forth. Your amplitude would be the distance from the equilibrium position here to either P or Q. Okay? Maximum distance from that. Okay? And the period would be how long it takes time-wise for you to go from Q through O to P and then back to Q again. One complete cycle. Well, what you would be doing if you were in the Ferris wheel, one complete turn of the wheel. And that's why they kept saying revolution of the wheel. Talking about the same thing. Okay? But your shadow would be going back and forth like this. That's what we call simple harmonic motion. That moving back and forth. It stops at this end, picks up speed, slows down, stops, picks up speed, slows down, picks up, yeah, back and forth, back and forth, back and forth, simple harmonic motion. Okay? Kind of a weird kind of example, but doable. Okay. Now, that's the last slide, but that's not the end of the story. So let's go back to the PowerPoint, to the whiteboard. Okay, and here's the formula you use. Now, I'm not going to type it in, so I'm going to draw it in because it has square roots and radicals and divisions and all sorts of things. So let me get my pad and my pen. Here is the formula for, there we go, okay, the period T, okay, probably I should have put those in. Amplitude, usually you use A for that, okay. Period is always capital T, and frequency is little f, okay. So the period here, capital T, is 2 pi. Now that always has to do with circular motion. 2 pi is the distance around a circle of radius 1, is 2 pi, okay, times the square root of, and under here is your L divided by G. Now what in the world is the L? Now we're talking about the pendulum. I kept talking about it. Here's what we're talking about here. Okay, this is so hard to see. It's almost impossible to see. There it is. There's your pendulum. Okay, L is the length of the line, the cord, whatever you want to call that, and your T is the period at which it's going to go. G is the acceleration due to gravity, just like it was in earlier chapters. And this is where that comes from. Okay? Notice what's missing here. At the bottom of the pendulum is usually a mass. The mass is immaterial here. It doesn't matter if it's a heavy mass or light mass. Whatever, it doesn't matter. All that matters is the length and the acceleration due to gravity. 2 pi is a constant. Square root's just an operator. G is a constant, so the period depends on the length. My parents-in-law gave us one of our first Christmases after we were married, a grandmother clock. It's like a grandfather clock, only smaller. And I never told them this. I could never get things to keep time well because it always was just a little, I can't remember now if it's fast or slow, but I wound the thing as far as I could, the pendulum, so to make the L just as short as possible, to make it go a little faster. I think it was. It never would work. I tried and tried. It was always, would lose about half a minute a day or something like that. So I always tried to, especially if they were coming, get it set right and hope they wouldn't stay too long to notice it was out. Okay, but that's the thing. Now, what is the G? The G is the acceleration due to gravity, 9.80 meters per second squared if you're in SI units, 32.2 feet per second squared, just like we used several chapters ago. Okay, so there's the pendulum. I probably should have put that definition in too. Excuse me, sorry. About this time of day, our AC changes, gets a little cooler, and now the fan makes it just a little too cool. So my wife says I'm crazy to sneeze when I get cool. She said most normal people don't do that, but I do. And I've lost my pen now. There it is, I found it. Okay. Oh, I don't need it. I'm going to type this in. I was going to type in the definition for pendulum too. So let me choose my text. I think my wife's home now. Okay, so here's the definition for pendulum. A pendulum consists of an object suspended so that it swings freely back and forth about a pivot. Okay, and that's what I was showing you in the picture. The pivot is the thing up at the top from which it's held, and then the length of that is the length of that suspended object, and it swings back and forth. The period would be from here to there again, back to the same position, from here back to the same position in the same direction. Just because it comes back to this position here, it's going in the opposite direction, so you have to come back to the same direction. That's the period, the time it takes for that to happen. All right, now I think we're ready for our examples. How are we? Oh my goodness gracious, we ran out of time. Sorry about that. So we're going to have to pick up with example 1, which is the only example that we have under 16.6. That's the last example in the section. The glossary comes next, then there's formulas, quite a few of those, review questions, conceptual type things, review problems. If you haven't had enough problems, do some of those. So there is a really interesting, and this actually occurred, example of resonance that we talked about before. A bridge was actually built in the Tacoma Narrows, which is near Portland, Oregon, I think it is, the Tacoma Narrows Bridge across the Puget Sound in Washington, not Oregon, but Washington, but it's pretty close. And it happened to be the natural frequency of that bridge was the same as the prevailing frequency of the wind. And it got to be when the wind was blowing very consistently in one direction, that built up resonant frequency, the bridge actually started rocking and rolling and actually tore itself apart. That is an actual picture of the bridge disintegrating because its natural frequency, its resonant frequency, was the same as that of the prevailing winds coming from the west. So it's really rather bizarre. But anyway, that's there. So, now I've got a question for you. Do you want me to go on and put the Chapter 16 test out there so you can start working on it even though we don't have that last problem done? Yay or nay? Okay. I will do that. It won't be immediate. I've got to take a little bit of time to get that. I think I already have it prepared, but I've got to find it and get it out there. So I'll put it out there on Blackboard under Messages. And next time, on Thursday, we'll start Chapter 7. We'll finish Chapter 16 and start Chapter 17. So let me go back and place my things in place. And you can't really do too many of the 16.6 yet until we do that example. You can if you want to, but we'll pick up from there, and then you can start working on your test until you get down to that portion, and then pick that up later. And then we'll finish that one problem, and then start Chapter 17 on Thursday. All right, and guess what, folks? 1 week from Thursday is the last class, okay? Which means that 1 week from Thursday, I'll be giving you your final exam, which will probably be just Chapter 17, and as much as we can cover Thursday, Tuesday, and Thursday. Okay, that's all we've got for 17. We probably aren't going to get to 18. 18 is we're not going to do every section in 17. It's a long section, a long chapter. But 18, goodness gracious, it's long. 18 is magnetism. We're not going to get there. Sorry about that. I don't think we'll get there. If we do, then your final exam will be just 17 and 18. I don't know if we'll get that far, but we're not going to do all the sections in 17. In fact, I'll tell you now which ones we will be doing. We'll be doing 17, 3, 4, 5, 7, well, actually got to do 6 to do 7, 8, and 9. So there's 7 sections there. Some of them are fairly short, but we're going to go just as quickly as we can through those sections and try to get as much of 17 done as possible. If we do any in 18, it'll be 1 and 2. Okay? But we'll see. I doubt if we'll get that far. We'll see. Any questions? Then one more. Say again? Okay. The one coming up is test 4, I believe. Wait. The one I'm going to give you tonight is test 4, right? Okay. And then we'll have test 5 will be 17. And if we do any in 18, I may have a question or two on that. So we'll do as far as we can. So that's all we're going to have. Normally, but you see what happened. They shortened our summer term. It's supposed to be 10 weeks. We're basically going to have 8.5 weeks at the max. And that last day is supposed to be finals day. What I'm going to do is give you the test. And so the one I give you tonight, please try to have it done by next Tuesday. And then the one, or you can take till Thursday if you need to. But Thursday I'm going to be giving you your last test. And that one you have to do Thursday, Friday, Saturday, or Sunday. So you only have 4 days on that last one because grades are due by noon on that next Monday. That's Monday a week away. So that last test, I'll try to make it short. I'll try to make it sweet so you can get it done fairly easily. But you'll only have 4 days to get it done. What's left of Thursday, Friday, Saturday, Sunday. So basically 3 days and a few hours. Okay, that's all. Sorry about that. It's just so crowded at the end. We were supposed to go until early August, but we couldn't because the whole school, in fact, the whole school system, whole state of Alabama is going to a brand new operating system. We've been doing under an old system called Alliant. We're now going under a new system called Banner. And so everything with Alliant has to be over with before the end of the month. And everything, if any of you are registered for spring term, you're using the Banner system. It just started this week. But they're going to have the Alliant system just till the end of the month. Then it dies. It's over with. No more Alliant. And that's what we have to enter the grades by because that's what we've been doing everything on. But then beginning in August, everything will be Banner and no Alliant whatsoever. So that's why they're having you register for your classes now in the new Banner system. Now, if you did it under the old Alliant system, they've already made the changes. And most of the time they did it right, but you'll have to check that. One of the advisees I had today, she didn't put that schedule in. That was somebody else's schedule, but they put it under her name. So we had to, I couldn't make any changes, but I told her what she had to do to change it. So there are some problems. Another one that I had today, she had changed her major last spring, but when they did the new system, they put the old major in. They didn't use her current major. So she's going to have to get them to do that. I couldn't do it. I tried, but there's no way I could make the change. So that's what today's been like, trying to advise students with a brand new system that is very difficult. It just started yesterday. So if you haven't already registered, you're going to be registering under My Lawson. That's what you use. No longer use Student Suite. It's My Lawson from now on. Okay? Any questions, comments? Okay, I'm going to stop the sharing. And unless there's some questions or comments, I'll end the whole session. Okay? Well, I heard no objections, so I'm ending the meeting. Have a good couple days. We'll see you on Thursday evening. Okay? Bye-bye.